Guess it's time to start. All right. Couple things first. Just a couple things. Where'd you go here? So, a reminder to everybody to, when you have a few 5 or 10 minutes, to please fill out the survey to evaluate the course. It's relatively brief. It's anonymous. And then I will also mention that I posted the final review that's on Grant's website. So if you looked at Grant's website, this is nothing new. But if you haven't, there's a final review from Grant right there. And then there's also solutions. There's 4 different files with solutions because they're broken up. So there's like 45-ish questions on there, I think. No, 50 questions on there. So there's a wide variety of things on this review. I encourage you to look at it. That said, I don't remember what I said on Wednesday as far as like what we were gonna do today. So sorry. Um, I feel like I probably said something like we should talk about what's gonna be on the final. It sounds like what's something I would say. So what's gonna be on the final? Everything. All right, but what is everything? Well, this is where it's, I think, a really great time to, where'd you go over here? Somewhere over here. To look at the syllabus, which is on the Math Part website, right? You guys know where the syllabus, you guys know where you can find the syllabi? Some of you guys, so just so everybody knows, just because I think it is worth knowing, if you maybe not. Sorry, I can't see my cursor. If you look at the math department website and you go to courses and you scroll down to syllabi, and then you scroll down and you look at undergraduate lower division syllabi. Right here, you can find the syllabus for Math 17B and all your other classes as well. And you can look at it and actually it shows you, okay, these are the things you should be going over in class. Now, that's not to say that your instructor is going to cover all these things or not cover something extra because instructors can do whatever they want. But that said, they should pretty much stick to this. So if we look at the syllabus here, just to kind of get an idea of what we have to think about, here's what we're looking at way back when. Oh yeah, all that stuff. We have essentially integration, right? That's kind of a big deal. Sure. The fundamental theorem of calculus also goes along with that. The thing I would remind you about this, right? So that's the thing that says the derivative of the integral from a to x of f of t is equal to f of x. Then we have all the methods of integration, which there are a lot of. The ones that come to mind, slash looking list. First and foremost, U substitution. If you're integrating something and it's not straightforward, that should always be the first thing you try to see. Is there a good U sub I can do? After that, integration by parts. And then we have all the other things. We have partial fractions. Fractions, I can spell fractions. And then there's like improper integrals as well. And then we have like kind of the physical stuff. We have area and volume. We have like modeling. Yeah, sure. Okay. So, and then, oh yeah, the quote unquote applications to biology. That's always a fun one. Ooh, I just thought of something. I think this is where we also have like the survival and renewal. I guys remember that? Yeah, okay. Um, I wouldn't imagine anyone expects you to memorize that formula. It's a terrible formula to memorize. I probably know it, having done it for years and years now. I think it's finally stuck in my head, but like you should ask your teacher if they expect you to know that, I guess, is the thing I'm trying to say in a lot of words here. Um, okay, after that, we have what I think it was the chapter 7 stuff. So yeah, essentially differential equations. And I would kind of think of there's maybe 3 things you really need to know how to do with differential equations. The first thing being just setting up a problem. So setting up a differential equation to model the situation that's been described. And then we only know how to solve 2 types of differential equations. It's either got to be, if you're solving it, a separable one or the first order linear. That's it. So if you see a differential equation that you're trying to solve, try to separate it. If it's not separable, then try to write like a first order linear. If it's neither of those, it should be one of those, right? It's neither of those. Either someone made a mistake or you've read the question incorrectly, right? Maybe someone threw a differential equation at you, but asked you to be like, is this autonomous or non-autonomous or pure time? And you started trying to solve it, but it wasn't solvable based on the methods we have. So that's a really good reminder to read the questions on your exam. Read the questions. I'm going to say one more word. Read the questions slowly and make sure you comprehend them. Probably one of the best pieces of advice I can give for any test taking environment is make sure you read the questions slowly and carefully. Yeah, and carefully. That's the other word I'm looking for. Yeah, direction. Okay, fine. There's a few more things in here which are not everyone's favorite. There's Euler's method. And then there's direction field. You can tell how much I love them by the tone of my voice. And then let's see what I have lastly here. Oh yeah, and then all the chapter 8 stuff. And then the chapter 8 stuff, which is all the vector and matrix stuff we've been doing lately. So vectors and matrices. So that's like all right. Yeah, I mean, I feel like there's a lot to say there, but we've got the dot product. We've got angles between, actually, so we've got projections. We've got matrix multiplication. We have inverses. And then we have the whole eigen stuff, right? Eigenvalues, eigenvectors, all that jazz. So not a small list of things to be responsible for making sure you're able to do on an exam. Sorry if the writing looks especially terrible over there. Maybe it's a little easier to read zoomed in a tiny bit. So, oh, and then, yeah, I guess the last thing, right? And then the last thing being the iterated matrix multiplication. Or in other words, a matrix raised to a power. So then, if there's anything I can clarify here, please. I see some of you like squinting, like, what the does that say? So if there's anything, I imagine you're looking at this part here, which is hard to read. If you want me to clarify anything, please ask while I take a sip of water. Good? Okay. Matrix multiplication. Yeah, I know that's matrix mult is actually what I wrote there because I abbreviated multiplication. Yeah. So that said, what should we spend the next 40 minutes doing? Oh, sure. So, what if I wanted to find the area between f of x equal to 2x plus 1. Oh, sorry, I zoomed in. X equal to 2x plus 1. And I didn't think about this super clearly here. Let's see. Sure. Sorry, I was trying to think of something cool, and now it's not going to be that cool. So let's say we've got f of x equal to 2x plus 1 and g of x equal to 9 minus x squared on the interval from 0 to 2. That might have actually worked out all right. Yeah, actually, scratch that last part. That's more what I wanted to ask. I was just worried the numbers weren't going to work out very well, but they are going to work out fine. So find the area between these two functions. Do we need to draw a picture? No. Could you draw a picture? Sure. But for just the area between two functions, you really probably don't need to draw the graph of it. What we do need to do is find where the two functions intersect each other if we're not given an interval to find the area over. So first things first, find the points of intersection. There should be at least two. There might be more. So we're going to set the two functions equal to each other. That's going to be 2x plus 1 equal to 9 minus x squared. Bring everything to one side. I'm always going to pick the side that makes my highest power of x have a positive coefficient. So I'm going to say x squared plus 2x, and then 1 minus 9 is minus 8 equal to 0. If the problem is well thought out, this should factor. If it doesn't factor, quadratic formula. But this does factor. It factors as x plus 4 times x minus 2. So our points of intersection are x equal to -4, and x equal to positive 2. So over here, when we're about to find the area, we know that we're going to be integrating from a lower limit of -4 to an upper limit of positive 2. And then there's two ways you can handle this next part. The way I would prefer, because I think it's better, but it doesn't actually matter, is you should actually figure out which function is bigger. You should pick any point between -4 and 2. I'd pick 0. and plug it into each of these functions and see which one's larger. Oh, let's see. F of 0 is 1. G of 0 is 9. So clearly G is the bigger function. So when I do this integration, it should be G of x minus f of x. If you don't do that, that's okay. If you accidentally get them wrong, you can just slap absolute values around the whole thing and then say the answer is whatever it is. It's technically valid. It is not wrong to do that. I just don't think it's as nice. But your teacher might be totally fine with it. I mean, your teacher might also not be fine. Your teacher might expect you to do this. So I don't know what to say about that, other than I would do it this way. So then we actually calculate g of x minus f of x. So that's going to be 9 minus x squared minus 2x plus 1. I don't think you really need to simplify the insides of this integral here, but there's nothing, it's not bad to do so. So I would probably first simplify this as the integral from -4 to 2 of negative x squared minus 2x plus 8. By the way, whatever you get in here will either be whatever you had here set equal to 0 or the opposite of that. In this case, it's the opposite, right? It's the negative x squared minus 2x plus 8. But you know that it's always going to be one of the two things that you're looking for. The rest of this is pretty straightforward. We anti-differentiate the whole thing. We get negative x cubed over 3 minus x squared plus 8x evaluated from -4 to 2. And then we plug in and we get -2. Let's be smarter about this. We don't need to write 2 cubed. Let's write 8. So -8 over 3 minus 4 plus 8 times 2 is 16 minus -4 cubed is negative 64. So that's positive 64 over 3 minus 16 plus 8 times -4 is minus 32. And I would stop there. Even if the problem said to simplify it as much as possible, I would still stop there. And then if I had time, I would come back. But that's good enough for most people. Yeah.
Building off this, could we also like talk about, I kind of forgot a little bit, like the different methods to do area and volume? If that, I remember, isn't there was 2 methods that we learned. It was like washer and this.
Oh, sure. So I would tell you that yes. So yes, I will also say that in most teachers' minds, the washer and disk method are the same method. Those are the same thing. It's just one is a special case of the other. So the disk method is the special case where your inner radius is just 0. Whereas the washer method is the more general case where your inner radius can be whatever. So, sorry, when you said 2 methods, I was like, we didn't talk about the shell method. That's not covered in this class. But, right, so yes, 2 methods, but really the same method, just one with an extra piece. But yeah, let's talk about that. So, yeah. So let's say we want to find, which way do we want to go here? Yeah, let's find the volume of the solid obtained by revolving the region. Let's see, how terrible do I want this to be? Sorry, give me 1 second here. Yeah, that's fine. That's fine. That's fine. That's fine. That's fine. That's fine. Yeah. The region bounded by. Yeah, we'll do that. Y equals natural log of x, y equals 0, and x equals e. Around we will start with the x-axis. And I will say here, although it is possible to do these problems without drawing a graph, you're hurting yourself if you don't draw the graph, right? You're making it harder to do if you don't draw the graph. So you should draw the graph, like no ifs, ands, or buts. If you're revolving, first thing to do is draw the region that is bounded that you're trying to revolve. Okay, so I've got y equals natural log of x, which is actually the only curve that we're drawing here. It looks like this. It has an intercept at 1, 0. And then I have 2 other lines. I have y equals 0, which is the x-axis right there. And I have x equals e, which is a vertical line about-ish there. So here's x equal to e. This point of intersection, usually, if these problems are written by people, the points of intersections are relatively nice. That point there, well, if this is y equals natural log of x, oh gosh, can I get my point over here? If this is y equals natural log of x, and this is the line x equal to e, well, then they're going to cross when x equals e, and natural log of e is 1. Cool. And then this point, of course, must be e comma 0. So here's the region that we're trying to revolve. The region has to be bounded by all of the graphs that we said we're bounding it. This example doesn't really like lend itself to any other regions. Oh, it could be this one or this one. Here it's kind of like it's got to be that one. So we're going around the x-axis first. So are we using the disk method or the washer method? Well, if we revolve this thing around the x-axis, I don't think you need to draw the revolution. Like, I think you just need to draw the area and then the revolution. Like, I don't have a lot of great 3D drawing ability, but if we revolve this around the thing, are we going to have some inner part that's like missing? No, we're not, right? This thing is solid, right? It's there's nothing like that we're hollowing out from the middle. So this is definitely going to be the disk method because we're not, right? When we draw a strip. So, okay, when I draw this strip, it should be, if I'm going around the x-axis, should my strip be horizontal or vertical? Right, my strip should always be perpendicular to the axis of rotation. So here's my strip, and look, no matter where I draw the strip, it is touching the axis of rotation. That means it's got to be the disk method. Or you can say your region is flush with the axis of rotation, or you can say the axis of rotation is one of my boundaries. All three of those things are just another way of saying, oh yeah, we're going to use the disk method here because we're not missing anything from the middle. Great, disk method. So I always like to do it this way where I say, I like to think about what this little strip is doing, although you can skip this part if you don't like it. But I'm like, oh yeah, my disk is getting rotated around. So the volume of my disk, well, that's just a circle with some thickness. That's going to be pi times my radius squared times the thickness, which is a small change in x, which I like to call dx. In this class, if you're, well, I should say, if you're just using the disk or washer method, it's always going to be the case that the axis you're going around is the variable you're integrating with respect to. So if you're going on the x-axis, your integral better be in terms of x. If you're going around the y-axis, your integral better be in terms of y. Okay, so let's see what we've got here. So in this case, the volume of our disk is going to be pi times our radius is the height of the strip, which is the natural log of x squared. Okay, so trapped. So then we're going to integrate this volume from as far left as 1 to as far right as e. So our volume here is going to be the integral from 1 to e. I would put the pi out in front, the natural log of x quantity squared dx. This problem is not very kind. This is a challenging problem. This problem requires integration by parts twice, and there's no shortcuts here. So to integrate natural log of x squared, so actually, I'll point out, here's what I would do. I would ignore the 1, the e, and the pi for a minute. Be like, okay, I know this is a definite integral, but when my definite integral has more steps than I care to admit, I would rather write it as an indefinite integral. So I'm going to think about, okay, let's make life suck a little bit less. Let's just look at the integral of natural log of x squared dx. And I should just use another page because I know it's going to take up plenty of time. So looking at that, so this, in retrospect here, if I was writing a test, I probably wouldn't ask you to do this because I don't want to grade this, right? Like this, people are going to make mistakes here. But what I would ask you to do for this problem is set it up, right? So this is, so again, back to the point of make sure you read the instructions carefully because there's a non-zero chance that one of your volumes will be a setup and do not integrate kind of problem. People like to ask those kinds of questions because they want to see that you're able to actually figure out how to set it up, but the actual integration might be terrible or just end up being gross. Here, let's do it anyway. So you're going to let u equal the natural log of x squared. Your dv is going to be dx. All right, this is integration by parts, in case I hadn't said it. It's one of those weird ones, though, where your u is everything and your dv is just dx. There's not a lot of those. Like natural log of x and arctangent of x are kind of the only ones we really see that fit the bill, where you let u equal the entire integrand and dv is just the dx part. Here, your du is going to be 2 times the natural log of x to the first times the derivative of the natural log of x, which is 1 over x times dx. And your v is going to equal x. So then, writing out the formula, ultraviolet super voodoo, it's going to be x times the natural log of x squared minus the integral of v times du. Now, let's be clever here. If we multiply v times du, we can see that the x times 1 over x is going to cancel out. Let's also put the 2 out in front. So we get 2 times the integral of natural log of x dx. And now we have to do integration by parts again. You might have memorized the integral of natural log of x. If you have, good. It comes up enough, I think, that it is worth memorizing. But if you didn't, then we have to do integration by parts one more time. So u is going to be natural log of x, dv is going to be dx, du is 1 over x, dx, v is x. And then we're going to end up getting this now. The x natural log of x still sticks around. Sorry, x natural log of x squared still sticks around. Minus 2 times the entirety of my new ultraviolet super voodoo. So x times natural log of x minus the integral of v du. Okay, again, v times du is x times 1 over x times dx, which is just 1 times dx. So fully getting the answer here, we get x times natural log of x squared minus 2x natural log of x minus 2 times minus x is going to be plus 2x. I don't need to write a plus c here because this indefinite integral was just for my own use. You could write a plus c, but I don't need to. So then I should have not tried to cut off space here and just left room for this. Oh well. So then we're going to go back to this and be like, okay, we did it. It was equal to x times natural log of x squared minus 2x natural log of x plus 2x. And then we can say, great. So then this integral, our volume, is going to, sorry, I don't know why I'm keeping this on the board. You can't see it. The volume is going to equal pi times the integral from 1 to e of natural log of x squared dx. So that's going to exactly be pi times all of that, x natural log of x squared minus 2x natural log of x plus 2x evaluated from 1 to e. And then we do it. We get pi times, okay, e is not terrible. So this is where I would definitely encourage you to, if you have to evaluate this, to simplify as you go, right? Like, I don't want to write natural log of e. I want to write 1. So if you're plugging in something and it simplifies easily, just simplify it, right? Just like when I plug in 1, natural log of 1 is going to give me 0. So here I'm going to get e times 1 squared minus 2 times e times 1 plus 2 times e. Great, the 2 e's are going to cancel. Awesome. Minus, then I'm going to plug in 1. I'm going to get 1 times 0, great, minus 1 times 0, great, plus 2. So in the end of the process, my answer is going to be pi times e minus 2. Quick understanding check. Does that make sense? Is our answer positive? Is e minus 2 positive? Yes, it did, right? E is about 2.7. So yeah, so good. Our answer came out positive as it should whenever you're finding a volume. Questions about this before we go around the other axis? All right. Yeah. Okay. So trying not to lose on the papers here or my marbles. Around the other axis, same picture. So now around the y-axis. Same picture. I'm just going to draw the region here. And again, my picture might not be great. That's fine. So here we've got our point E comma 1. Here's E comma 0. Here's 1 comma 0. But now we're going around the y-axis. So we better use a horizontal strip. I should also write the functions again. Sorry. This is y equals the natural log of x. This is x equals e. This is y equals 0. And now you can see that the strip I drew does not touch the axis of rotation. Which mean or I should say because let's pretend like just for a second. I need to my I left my ruler somewhere and I know I still have it. I didn't lose it, but it's not where I need to be. So let's pretend for a second the axis of rotation was right. That's not the best, James. Come on. Let's pretend I'm trying to find something that fine. Let's pretend this is the axis of rotation right there. So like that corner was the origin instead of the point 1, 0. Technically, yes, you could draw one strip at the very bottom that touched the axis of rotation. But to be the disk method, to be flush, any strip you draw has to touch the axis of rotation, which means you shouldn't draw it at the top or the bottom. You should always draw it in the middle or left, right in the middle. So since that strip doesn't touch the axis of rotation, we know it's not going to be the disk method. It's going to have to be the washer method because when you rotate that thing around, you're going to be missing this whole middle part. All right, there's my big old washer. So when I'm trying to find the volume of my washer, I'm thinking, great, it's going to equal the big area, so the area of the larger circle, pi times big R squared, minus the area of the smaller circle, pi times little r squared, times the thickness, which is dy. And that's your big radius. That's your small radius. So the big radius is easy here. The big radius is just E. Right? It's always going to be E from the axis to the line x equals E. The small radius, on the other hand, depends on how high or low you are. So it's going to be how far it is from the axis to this function. But it would be incorrect to say that the small radius was the natural log of x because we know our integral should be in terms of y. So it's always the case that if you're going around the y-axis, you have to write your functions in terms of y. So your y equals natural log of x is going to become x equal to e to the y, which is preferable. E to the y is much easier to anti-differentiate than natural log of x. So great. So then the volume of our washer here is going to be, let's factor out the pi. It's going to be the big radius squared, which is just e squared, minus the little radius squared, which is just e to the y squared. Great. So then the total volume is going to equal the integral from how low my strips go to how high my strips go, which is as low as 0, as high as 1, right? The y value of that point, not the x value of that point. And then we put the pi on the outside, and we've got e squared minus e. So e to the y squared is e to the 2y. All right, here's where we have to be a little bit careful, not because it's hard, but because it's easy to make a mistake. The antiderivative of e squared isn't just e squared, right? Because that's a constant. And the antiderivative of a constant is the constant times your variable. So in this case, we're going to get pi times the integral or antiderivative of e squared is e squared times y. And then the antiderivative of e to the 2y is e to the 2y divided by 2, or multiplied by 1/2, from 0 to 1. So if you were given your choice of which problem to do here, the second one is by far the preferable one. Right? It is much, much easier to do the integration of the e thing than the natural log thing. Not that you get to choose, but if someone gave you a choice, you should choose this, even though it does require the work of switching like what the function looks like and going around the y-axis instead of the x-axis. We plug in, we get pi times, let's see, e squared times 1 is e squared, minus 1/2 e to the 2 times 1 is just 1/2 e squared. Something minus half of itself is going to be half of itself, minus e squared times 0 is 0, and then 1/2 e to the 0 is 1/2. So we're going to get pi times e squared minus half of e squared is half of e squared minus minus is plus 1/2. I would probably leave it like, excuse me, like that. But if you really wanted to, you could factor out the 1/2 and say it's 1/2 times pi times e squared plus 1. But I don't think that's necessary. I would leave it like this. On a test, you should probably stop at the step before that. You should stop here and then come back later if you have time. For integrals, I'm really, really a fan of stopping after you've plugged in your limits of integration. I should say, for definite integrals, I'm a fan of stopping after you've plugged in your limits because essentially you've got the right answer, you just haven't simplified it. And then if they say you should simplify it, then you should simplify it if you have time at the end. But if they don't say you simplify, or if they specifically say you should not simplify, then you should not simplify. I'll say it again. Read the instructions on the exam. I can't say it enough. Read the instructions on the exam. I can't tell you how many times I've seen students do the wrong thing on exams and waste so much time because they did not read the instructions. So please do me a favor, do yourselves a favor, read the instructions carefully, slowly, make sure you understand the words that are written there. They're usually there to help and not to hinder. Okay, that was some area and volume. What else in the last 15 minutes here? I have an idea if you don't have anything. Like a tank problem? I like a tank problem. But we can do something else if you don't want to do a tank problem. But seeing no requests. All right, here we go. I should ask, did everyone do tank problems? Where you put like stuff in a tank and it drains out at the same rate? No? I see some people, yes, some people no. I guess we probably shouldn't do a tank problem if not everybody did a tank problem. Hmm. Sure. Then what else should we do? There's so many things to do. Yeah. Oh, okay, sure. Can I find? Yes, if I can find one on this giant list here, because they're not problems that are really easy to make up. Where'd you go? Let's see here. We've got lots of pages and they're all over the place. Where'd the other pages did this go? Sorry. I should have brought my textbook, but I should have done. Let's see. Is there a survival renewal problem in here? Unfortunately, I don't see one. That is a little surprising. Yeah, I don't. Sorry, I don't have one. Let me actually, you know what? I can grab one real quick here. One moment. Just give me, see if I can find my cursor. Why don't you want to open up a new window? Oh, there we go. Why are you over there? Sorry. Let's see here. I do actually have the book available to me, but let's just do this instead. All right, let's see here. All right, here's a problem we could do. Yeah, all right. I feel like I will point out most of these survival renewal problems are just making sure you know how to put things in the right place, to be really honest. So let's say we've got this situation here. A population. I don't love this pen. That's not true. I really like those pens, but people don't like how I write with them, so it's fine. A population of insects currently numbers 22,500 and is increasing at a rate of 1,225 e to the 0.14 t insects per week. If the survival function is S of t equal to e to the negative 0.2 t, where t is measured in weeks. I'm not going to write that down. How many insects will there be after 12 weeks? Okay, so we have to remember what the formula is. So here is the survival and renewal formula. It's the population at however much time has passed, which is represented by a capital T, equal to, do I remember it? Let's see, I know, not really. It's equal to S of T, the survival rate after that, however much time has passed, multiplied by the initial population, P naught, plus the integral from 0 to T of your survival function evaluated at T minus lowercase t, where lowercase t is your variable, times your rate of growth function, or your rate of increase function. So there's your survival function, which are your survival renewal function. So let's identify all the things. In fact, yeah, no, we have limited time. So here's what we need to identify. So P naught is how much we're starting with, which is 22,500. We're increasing at a rate of 1,225 e to the 0.14 t insects per week. That's our R of t. So R of t is 1,225 e to the 0.14 lowercase t. They told us what S of t was. Great. So S of t is going to be e to the negative 0.2 t. And finally, capital T is the amount of time we're talking about having elapsed, which in this case is 12 weeks. So now we need to take all that and jam it into the equation here. And I would point out it's probably worth your while to, instead of having to think about what this is, write it out down here. So S of capital T minus lowercase t is S of 12 minus lowercase t. So we're just going to replace the t here with a 12 minus t and get e to the negative 0.2 times parentheses 12 minus t. That part always feels like just a little bit weird, so I would recommend doing that. All right, so now let's actually write what we've got down. So P of 12, I'm replacing every capital T with a 12, is equal to S of 12, which is going to be e to the negative 0.2 times 12. We probably could have done that multiplication, but I didn't. Times P naught, which is 22,500, plus the integral from 0 to 12 of our S of t minus t, which we just said was this down here. Now let's actually simplify this a little bit more. That's going to be e to the negative 2.4 plus 0.2 times t. And then our function there is that number there, that function, 1,225 times e to the 0.14 t. I don't know why I put parentheses around there. I just did. No good reason for that. Those parentheses do not need to be there, but fine. So there it is. That's the whole thing. The rest of this is then just doing the math. So let's simplify it a little bit. We shouldn't spend too much time here, though. I would write this as 22,500 times e to the negative 0.24, negative 2.4, apologies. Right, 12 times 0.2 is 2.4. And then let's bring out the 1225. And let's also bring out the e to the negative 2.4. That is also a constant. We're left with the integral from 0 to 12 of e to the 0.2t times e to the 0.14t, and we can add those powers together to get e to the 0.2 plus 0.14 is 0.34t. The rest is pretty straightforward. I mean, the numbers are not nice, but the rest is straightforward in that you integrate this, you're going to get, I would probably choose to write this as 22,500 divided by e to the positive 2.4, just because I think it looks nicer. Same deal over here, 1225 over e to the positive 2.4. And then we integrate that and we get e to the 0.34t divided by 0.34, evaluated from 0 to 12. You plug in the 12, you plug in the 0, subtract, and that's the whole deal. On an exam, hopefully the numbers will be nicer. But that's kind of what you do. That's not a question I know the answer to. I mean, so my get, so most of the time I've seen in the past, people supplied that equation, but really it's a question if you're concerned about, you should ask your instructor. Do we need to know the survival renewal equation, or will it be provided, or are you even going to ask a question about it? Usually probably leave off the last part. Like you should just say, do we need to know it, or are you going to provide it? And they should. I mean, they might be cagey and be like, I can't tell you what's going to be on the test, but what you got? Cooper, Carano, or Challenor? Those are the teachers. I feel like most of them are pretty straight up. So I feel like any one of them would probably tell you yay or nay if they were going to give it to you or not. But I can't say for certain because I'm not. So what else? What about oh question.
I forgot. So, from the in lecture where it wasn't technical from like, you know,
The first order linear differential equations? Yeah, sure. Let's do one of those. Mm, yeah, do I love the examples I have here? Sorry, one moment. Sure. Yeah, let's do this. So let's say we have the following differential equation. I'm going to take one of these tank problems and just kind of set it up without the tank part. So yeah, so here's what we have. We have that the rate of change of something. I don't love this situation though. It's fine. Oh, sure, we can do that one. So dsdt is equal to, yeah, I'm going to change this up a little bit. So, sorry, I have to actually think for a second here. We're putting in, sure, we're putting in water that is, yeah, it's fine. 4 gallons per minute. So 4 times, sure. Yeah, 4 times 2. Sorry, I know this looks silly the way I'm writing it. I promise you it's not as bad as it looks. Minus what we're taking out, which is going to be S divided by 100. Sure, okay. Sorry, here's my weird looking differential equation. So I will point out that this differential equation could be done separately. So I think it's worse though. And I will admit it is taking me a few years to come around to this way of thinking. In the past, I might have said you should always separate because I feel like it's easier. I no longer feel that way. I feel like sometimes the first order linear way of doing things is the easier way. Because the integration here is not particularly nice if you try to separate. If you were going to separate this, I'll just point, and yeah, we got enough time. So if you want to do this a separable way, here's what you should do. You should rewrite this as ds dt equal to, I should have just written 8 here, but let's get a common factor or common denominator. Say we have 800 over 100 minus s over 100. And then you would separate by saying 1 over 800 minus s ds equals 1 over 100 dt. Integrate both sides, solve for s, and so on and so forth. But it's not so nice because solving for s here, you're integrating this, you're going to get the negative natural log of 800 minus s, and then you have to bring the negative over and e both sides and all that stuff. So not my favorite. Instead, I would recommend, especially because it's kind of already written in a way that's making you think first order linear, right? You've got your derivative and your something times your s and your other thing. So I would really go first order linear here and say, well, great, I'm going to write this as ds dt or s prime if you prefer, either way, plus this part, which is 1 over 100 times s equal to 8. Great, I've written it in the usual way. And I know this one's a little bit funky because my P of t is just a constant, and so is my Q of t. That's okay. So then after we've written it in the standard form, which is your y prime plus P of t times y equal to Q of t, or whatever variable we're using instead of y. I'm using s in this case instead. Then we're going to say, man, we're going to say that our integrating factor, which you might have called mu or you might have called I, is equal to e to the integral of p of t, which in this case is e to the integral of 1 over 100, which is e to the 1 over 100 times t, or t over 100. And then how much work you have to do here is variable. Some people just want you to jump to the answer. Some people want you to show all the work. I like showing all the work. So I'm going to show that I'm going to multiply everything by this integrating factor. So I'm going to take my equation and multiply everything by e to the t over 100. So I've got e to the t over 100 times s prime plus e to the t over 100 times 1 over 100 times s equal to 8 times e to the t over 100. The thing your teacher is most interested in you showing that you understand here is that the left-hand side is the derivative of a product. That's what if they want you to show all this work, that's really what they want to see, is that you know that all of this is really just e to the t over 100, or whatever your integrating factor is, times your function s, the derivative of that product. That's what they really want to see you are aware of. Still equal to the same thing on the other side. And then we solve the situation by taking the antiderivative of both sides. So on the left side, the antiderivative of the derivative is just going to be e to the t over 100 times s. On the right side, we're going to actually integrate 8 times e to the t over 100. Wrapping things up here, we integrate the right-hand side. So we get e to the t over 100 times s, or if you prefer, s of t. And that's equal to, when you integrate this, you're going to divide by 1/100th or multiply by 100 and get 800 e to the t over 100 plus a constant. And it is vital here that when you finally solve for s of t, that constant is getting divided by this piece here. So you have 800 e to the t over 100 divided by e to the t over 100 plus c divided by e to the t over 100. Or as I would write my general answer here, s of t equals 800, because those cancel, plus c over e to the t over 100. And then if you had an initial condition, you could plug in your initial condition and solve for c. All right. Again, a reminder, two reminders. Reminder one, please fill out my evaluation. Reminder two, read the questions on your exam. And then reminder three, I have office hours next week. They're all in the library and drop in. I posted them on Canvas. It's like every day, 11 to noon and 1 to 4, except for Thursday. I won't be there 11 to noon, but I will be there 1 to 4. So if you are looking for me, that's where I am. That's where all of us are next week. So don't look for any of the specialists at any other place other than the library, because that's where we'll all be. Along with, no, this is the last day of class. There's no classes next week, just finals, no classes. That's always how finals are. Today is the last day of instruction. And good luck. I hope it goes well. And I'll see you all next quarter for 17C if you have to take it, which most of you probably do. You're welcome. If you're taking 17B, you usually have to take 17C. You're welcome. And I'll be over in office hours as usual. You're welcome. If someone could bring up the attendance sheet, I'd appreciate it. Bye, you're welcome. Yeah. Yep, yep, just over in the usual spot. I'll be over there in a few minutes. Welcome. Everyone's welcome.